so we're back again, back to geology. Geology, of course, extremely important component of geography. It's not just how humans use it, but also what are the resources, where are they at, what are the relations. And geology explains a lot of that. Mineral locations such as lithium here in South Arkansas, oil in South Arkansas. Say a lot of these mining companies and oil companies, they hire geologists to find exactly where this stuff is. Gold mines, silver mines, that's also a thing about geology. And also, geologists, they also use to stake out locations for reservoirs, dams, and things like that. It's a very useful occupation. And knowing where these resources are, knowing how they're distributed, knowing the relationship between them, that is an extremely important part of understanding the world, understanding the economy, transportation systems, where we build, where we live, what we do, where we live. I left off last time, remember, the idea of geologic time. We're talking about extreme amounts of time, so it's kind of hard to really put it in terms we can kind of understand. We can see the numbers, we understand the numbers, but understanding kind of what that means, it's a kind of mind-boggling. The Earth is approximately 4.6 billion years old. It is ancient in the extreme. And this is done by years of studies. And you have to remember about scientists is they're competitive. If one of them was wrong, they would call other scientists are very happy to call them out. But all the studies, everything's pointing to this number. It's a cool number, but it's not one they just picked at random. Scientific insight showed it. And all these geologic forces of uplift and erosion, rock formation and decay. Actually, these forces aren't just at work on Earth, but in the other rocky worlds of the inner solar system. Mercury, Venus, Mars, the Moon. There actually are quakes on the Moon, moonquakes. They do measure those. Like I said, there are this volcanic activity on Mars, plate tectonics on Mars. Like I say, one of the moons of Jupiter, Io, is famous for its sulfur volcano eruptions. But here on Earth, we have a world that is constantly making and remaking itself. Slowly, but it is. So we're talking about the solid rock underneath of us. It's in motion. It's active. It's changing. Very slowly. But it is. Like I say, changes I wouldn't be able to see in our lifetime, even 100 lifetimes. But those changes are there. Now let's talk about the idea of continental drift. Because rocks beneath our feet, they are in motion. It's the drifting, colliding of continents over millions of years. Theory is originally developed by a German geologist, Alfred Wegener, proposed that the Earth was once one supercontinent that broke up and drifted apart. This idea here was, you look at a map of the world here, how they do kind of seem to fit together. How you twist South America here can kind of fit here with Africa. The little hooker part of Antarctica can fit with Southern Africa. So forth. And even North America connected with Europe. In fact, it's one of the interesting things about continental drift is The mountains here in northern Scotland, the Scottish Highlands, are part of the Appalachian mountain chain. Because Europe and America were once joined together millions of years ago when these continents were forming. But as it split up, one part of the mountains is here in Scotland. Here we have here from New York down to Georgia. And they study that by looking at the similarities in rock formations. And the Pangea theory was the idea of all Earth. That's what Pangea means. All land masses, one continental location about 225 million years ago. So go to your book maps here, book here on page 50 on chapter 3. Kind of see how the theory works, that Pangea starting here and kind of slowly splitting apart. Closer here. But yes, gradually breaking into two larger land masses about 135 million years ago. About 65 million years ago, you have North America basically separating from Europe. But it takes several million years for South America and North America connected. But as it's breaking apart, like the ocean started filling in here, the formation of the Gulf of Mexico. And while that process is happening, about 100 million years ago, about 50 million years ago, where we're standing here in South Arkansas was ocean. And we're part of the Gulf of Mexico. You got to remember, this is taking place over millions and millions of years. Changes are slow and subtle, but they're there. And the process is still continuing. Say 65 million years ago, Canada and Greenland were joined together with Northern Europe. Australia was joined with Antarctica. The Atlantic Ocean was only beginning to form. The process still going today. 50 million years into the future, East Africa split off, extend eastward into the Atlantic and the Indian Ocean. In fact, they can see that today. This area here of East Africa called the Great Rift Valley. Forces are pushing Africa apart, and the continent, part of the continent, moving eastward. India was once its own little separate area, but it started moving northward and collided with Asia, pushing everything upward. Basically, it's like pushing two things together, they push up. There's nowhere else to go. And that created the Himalayan mountains. And the Himalayas are still growing today. Why? Because India is still pushing into South Asia. Now, the largest geologic feature on the planet is the Mid-Atlantic Ridge. It's very active, runs roughly right along in here, cutting through Iceland and kind of jagged here at the middle Atlantic Ocean, moving down towards Africa. And from here, forces far beneath the earth are pushing rock upward. It moves up and out. And that's why Iceland has so much volcanic activity today, because that magma being forced upward from beneath the surface through the Mid-Atlantic Ridge. Iceland is a fairly new island, but it's formed because of those processes of the Mid-Atlantic Ridge. And Mid-Atlantic Ridge, because it's spreading out, it's forcing all these continents away from each other. So the Atlantic Ocean is getting larger and larger and larger. So what's the rate of continental drift? About 2 to 3 centimeters per year. Not much, but they can see it. But again, it's not anything we're going to see in our lifetime. Give an example of deep geologic times, how far we're talking about. So 2 to 3 centimeters, that's about an inch a year. Now suppose we start from here in El Dorado and move south at the rate of an inch per year. In 1 million years, we will reach Junction City, 15 miles away. Yeah, Junction City is 15 miles, that's 1 million inches. That's how far. That's how slow this process is, but it's happening. They can measure it, they can see it. But even in 1 million years, you wouldn't see very much difference. Even 500,000 years wouldn't see much difference. But it's there. They keep spreading out further and further. 1 million, 2 million, 5 million, 10 million. Pretty soon you start seeing more noticeable distances. Now the Earth crust is sitting on a series of plates. It's not all one solid rock surface. There are little breaks in it here and there. And how these move around is called plate tectonics. It's a really big thing in geology, plate tectonics. You can hear page 51 of the book, see some of the different geologic plates here. For everyone viewing at home. But as you can see, the Pacific Ocean itself is basically one huge plate. And what it's doing is basically it's spinning counterclockwise. Now, not all of it is underground. Some of it is above ground as it reaches California. And the North American plate, it's its own plate, is pushing steadily west. So it gets to the point it's running over the Pacific plate. And as they collide, what happens here in the western part of North America is the western part is being pushed up, forming the Rocky Mountains. So we see the Rocky Mountains here on these maps here. What's happening is it's running over the Pacific plate, North America. And that's why California is so prone to earthquakes, because that's where that fault line meets. That's where those two continental plates are meeting. And because the Pacific plate is basically spinning counterclockwise, that means is Los Angeles is slowly moving northward, right about an inch per year, about an average. Which means in 50 million years, Los Angeles and San Francisco will be next door neighbors. Assuming the city still exists by then. That's part of what's happening. So plate tectonics, this is how continents move, combine, and split apart. You've got three types of fault lines. Fault is basically the boundary line. Now, of course, as these plates move, of course, they're made out of rock, they're brittle, they crumble a little bit. It's not all one solid fault line. You got little breaks moving off to the side of it. And sometimes some ways away from the main fault line, but they're there. And because these rocks are grinding against each other, that builds up a lot of pressure. Pressure sometimes breaks and is released as an earthquake. Now, 3 types of fault lines. First, the convergent fault. Example of that is India and South Asia. 2 are combining into each other, creating mountain ranges like the Himalayas. So what's that mean in practical terms? Does that mean means mountains keep growing? So is Mount Everest going to keep getting taller? Yeah. Unless something stops India from pushing into South Asia, Mount Everest is going to keep growing. The same effect it have on Mars, the Mountain Olympus Mons. It's an extinct volcano, but the plate tectonics on Mars, there's nothing there to change it, so this mountain is already 15 miles high, the tallest mountain in the solar system, and it just keeps getting taller and taller over time. In different planet, but same physics works, same science. 2, the divergent fault line. So, Mid-Atlantic Ridge. In fact, you can actually dive off the coast of Iceland in the Mid-Atlantic Ridge area and see where the European plate and the North American plate meet. Right there in the middle of the Atlantic Ocean. Basically, it's this big trench there. But yeah, they're moving apart. Another example again, East Africa, the Rift Valley. Can't see anything yet. It's not filling in with water, ocean water yet, but one day it will. Many, many years from now, not in our lifetimes, not even our grandchildren's lifetimes, but it will happen. And third is a transformation. It's a transform fault. Where there's moving against each other. Example here, San Andreas Fault. Just sliding against each other. It leads us to our some of our websites here. Got here is the U.S. Geological Survey website, including the latest earthquake observations around the world. This right here, of course, being the San Andreas Fault. This is the North American plate, this is the Pacific plate. Where the Pacific plate is moving northward, North America moving west. So you can see where it comes in here. Up through the Gulf of California, east of San Diego, gets pretty close to Los Angeles here, and moves up right here towards San Francisco, moving north here toward Alaska. And yeah, we live on a very active Earth. Latest earthquakes. One was recorded at 9:56 Universal Time, about 3:56 this morning. 2.5 magnitude earthquake, 54 miles north-northeast of Chase, Alaska. And a depth of 81 kilometers deep. Small one, Hawaii this morning. 43 miles east of Nalihu, Hawaii. Yeah, they record these by depth because these aren't earthquakes happening on the surface. They're often happening deep, deep within the earth. Fairly solid one. 5.1 magnitude, 58 kilometers east-northeast of Laredo, Mexico. Depth of 10 kilometers. Now, the thing is about the Richter scale is these smaller ones, usually like under 3, you hardly ever feel them. They really don't cause any kind of real damage. 4 and 5, now you're talking damage. Remember, it's scale of magnitude, 10 times 10 times 10.
Isn't it logarithmic?
Yeah. And these are, like I say, and earthquakes happen all the time, but the thing is, you usually don't feel them. Again, this is the U.S. Geological Survey website, earthquake.usgs.gov.
I actually, whenever I was at A-State in late 2020, I actually slept through an earthquake.
Yeah. I lived in Austin when I was an undergraduate, and one of the things that happened then, while I was living there was there's a huge earthquake. There's an earthquake. It's from out in West Texas, but we felt it in Austin. And I'm laying down here in bed, and it just felt like a big truck running past my apartment building, just shaking. You didn't realize what it was till, that wasn't a truck, that was an earthquake. Oh. That's the thing about living in earthquake-prone areas, and here's the Mid-Atlantic Ridge here. But you live in these areas, you get used to it. Just like we get used to tornadoes in this area, because we know they don't happen very often. When they do, they're usually far away, not going to damage us. We have warning. We know how to prepare for it. Just like in California, they know how to react and prepare for earthquakes. Most of them are small, so it doesn't bother them, and buildings are built to withstand earthquakes. Because most of them are very small. Most of them you're not going to notice. But you get to magnitudes like 5, yeah, you're going to feel that. It might knock a few things off the shelves at the stores. 6, you got 6 and 7, you got problems. But yes, these are recent earthquake activity, especially here in the Pacific Plate area they call the Ring of Fire. All around in here. Now, Arkansas. You ever notice an earthquake here? We have them. Like I said, up in Jonesboro. The worst earthquake in American history is actually here in southeastern Missouri, the New Madrid earthquake. Because like I said, the continental plates, they're brittle. They crack and break. So we have a big break right here in southeastern Missouri. It moves in here into northeastern Arkansas. So yes, there are earthquakes here. This is a website called earthquaketrack.com. It says small earthquakes here and there, but 3 weeks ago there was a 1.7 magnitude quake in Caraway, 23 kilometers deep. 2 miles from Caraway itself. Epicenter 35 degrees, 34.7 degrees north, 9.3 degrees west. 3 weeks ago. month ago, another one near there, 1.7 magnitude, again 5-kilometer depth. A month ago, Walnut Ridge. It's near 2.0 magnitude, 15 kilometers from Walnut Ridge, depth 8 kilometers. And here 1.8, 14 miles from Highland, depth 4 kilometers. And you have what they call seismographs that measure these. Seismographs, they can pick up major earthquakes around the world. Earthquakes around here, think we're immune to them? Nope. And we got 2 weeks ago, it was a 3.5 magnitude near Coshada, Louisiana, 5 kilometers deep. It is kind of southeast of Shreveport. We've had some in our area before. They don't happen very often, but they do happen. In Union County, May of 2020, there was a 2.8 magnitude, 13 kilometers southeast of El Dorado, around about here near the state line, 11.8 kilometers deep. February 2020, 2.8 magnitude, 12 kilometers east-northeast of El Dorado, actually east-northeast of Junction City, excuse me, 14.3 kilometers deep. 7 miles from El Dorado, 3.0 magnitude, 16-year, May of 2007, depth of 5 kilometers. Yeah, some people could feel that one. If it caused any damage, people would notice it. December 24th, 1997, 2.6, 4 miles west of El Dorado, depth 5 kilometers. See a few here and there. And of course, what's going on today is you've got volcanic eruptions. Biggest one today was 5.8 magnitude in Vanuatu, that's in the Pacific Ocean. And a magnitude 1.5 or greater. 124 earthquakes in the last 24 hours. That's a normal day for Earth. Remember, the Earth is kind of like a big bell. You just kind of bang on it and it rings all over. That's how seismographs pick up earthquakes from hundreds of miles away. Remember, lots of things can cause these quakes. Not just fault lines, but atomic explosions, for example. During the Cold War, that's one way we could tell that the Russians were testing nuclear weapons was we could pick it up on our seismographs. We could read the pattern from all the way from Russia. – 1,300 earthquakes in the past 7 days. 53,000 magnitude 1.5 or greater the past year. And just normal. Things move around, things shake around. Areas where there's a lot of oil drilling or sometimes, yes, there is a lot of there's sometimes some quake activity caused by that because you're changing the pressure in the earth. And that sometimes causes those rocks to move around a little bit. Large-scale construction can cause small quakes. Cave-ins and mines, that can cause quakes. That can be Richter scales and so forth. Not as much as others, but you can see them. You can see most of the earthquakes, again, here in the Ring of Fire area, the edges of the Pacific Plate. Not so much in other places, but there are a few here and there. Now, most states have a state geologist. Arkansas is one of them. There's a very useful website here, geology.arkansas.gov. They tell you everything about the geology of the state. Except different things we have, different finds, fossils. Yeah, there actually were dinosaurs here. Not many, but there were a few. How geology relates to the energy industry. Of course, oil produced here in South Arkansas, natural gas, brine, coal. Coal is mostly in western Arkansas, lignite coal and so forth. Different types of minerals we have. The geohazards, earthquakes, landslides. So we have a few, but nothing too major. Could the New Madrid fault, which caused that eruption 200 years, that earthquake 200 years ago, could it have another one? Yeah, it's possible. Another serious one? Yeah, maybe. But there are a lot of places where earthquakes can occur. All that pressure has to, rocks building up against each other, has to find some way to that pressure to relieve itself at some point. That's why I talk about possibility of a major earthquake in Southern California. But can smaller earthquakes relieve some of that? Sometimes. Just kind of depends on the nature of the quake. But sometimes a smaller quake can lead to a major quake. Sometimes these huge quakes, they have earthquakes that causes earthquakes for days and weeks afterwards. Those are called aftershocks. XA, you can get maps from Arkansas State Maps. So the geologic map of Arkansas shows us kind of how we are here. Let's see if we download that. Anyway. Mining web map. Hazard maps showing areas of most likely to have serious activity in near the Jonesboro area, but mostly moving across the Mississippi River into the southeast Missouri. But areas like the Boston Mountains, Ouachita Mountains, you're not going to have a lot. Seismic stations in Arkansas. I got a couple of them here and there. And different publications. You can get fact sheets, maps, guidebooks, historical publications, and so forth from all over the state. Very useful information. That's from the Office of the State Geologist. Yes, Arkansas does have a state dinosaur. It's like 6 to 7 feet high. It's like a kind of bird-like. Can't find a lot of them, but the was there, and we named it the Arkansaurus for get educational posters and so forth. Our state rock, bauxite, state mineral, quartz, state gem, the diamond. Because Arkansas is the only state in the country where there is an open public diamond mine. The thing is, you got to know where to find it. Yeah, they do sometimes find some fairly solid ones, 2 or 3 carat diamonds. The thing is, they're not these nice, clean diamonds, shaped diamonds like you see on diamond rings at the jewelry store. So, guys, if you're planning on proposing and getting your girlfriend a diamond ring, say Crater Diamond State Park may not be quite what you're looking for. But you love digging in the dirt, yeah, that's the place to go. Just gotta know what to look for. I took a couple of my kids there years ago. Little kids, of course, like digging in the dirt. So, some of our geology sites. Okay.
A lot of earthquakes.
What's that?
There were a lot of earthquakes
enough, my screen has turned purple. Anyway. So plate tectonics. And again, we go back to the idea of what is the Earth made out of? Well, Earth is built in layers. The outermost area is called the crust. We are living on top of the crust. And that's about 13 kilometers, give or take. And you got the mantle underneath. Under the crust, that's because of all the heat and pressure underneath it. Rock turns to liquid. So yeah, 20 miles beneath our feet, it is solid lava. It is lava. Molten rock. Of course, because it's molten, that means it's in motion. And beneath that go away, it's got the outer core. And then the inner core. Of course, because this is liquid, what does that mean? What's heaviest sinks to the bottom. So you got a lot of heavy minerals in there, a lot of heavy radioactive minerals down there, uranium and so forth, down the outer core and the inner core. The inner core, because of the pressures, that liquid is now re-solidified, even in spite of the intense temperatures. So you've got a solid core made out of iron. And of course, as iron spins, what does that do? Creates a magnetic field. Shoots up through all this, up to the north and south magnetic poles. And out into space. Because the core is spinning. You created a magnetic field, which protects us from cosmic radiation. Otherwise, life as we know it on Earth would not be able to exist because of all the intense radiation from the sun. But because those charged ionized particles, they are deflected by the magnetic field. And sometimes they charge these particles up here in the north and south magnetic polar regions, creating the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere. The northern lights. Basically, that's the Earth's magnetic field interacting with the solar wind, all those charged ionized particles. So it's very pretty up north. We live a little too far south to see it, but sometimes there's like a big solar eruption, a bunch of charged particles moving across interplanetary space. Sometimes those really big solar storms can cause the aurora to be seen in portions of the northern United States. Rarely, but sometimes. You see it all the time in Alaska. Again, because that's spinning magnet deep beneath our feet. So the crust, it is a thin cover of rock on the Earth's surface and above the ocean floor. This is an area we call the lithosphere. Lithosphere. Which means a ball of rock. But basically, it's the area of solid rock at the outer edge of the Earth. crust on down to the magma beneath it, that is the lithosphere. And you get to the middle part of the mantle where it starts becoming molten, that is called the stenosphere. So, with the lithosphere, we have these 12 large and many smaller rigid plates, each of which either slide or drift above the molten layer. Because yes, you got this big ball of hot liquid rock beneath us, and the outer dry part that's cooler, just kind of floating on it. Because it's floating, it means it's also in motion. Very slowly, but it's there. "12 large plates scattered across the earth." Now, why plate tectonic works, the most plausible theory is convection. Warmer, lighter rises, cooler descends. And you see that here again on page 51. That is, for example, where the Pacific plate and the Asian plate meet. What happens is you have what they call a subduction zone, where the Pacific plates literally just goes underneath the Asian plate. And what happens is it goes underneath here, underneath the plate into the mantle, the rock melts. And of course, what happens is rock melts, part of it starts bubbling up through the core, through the crust, and causes volcanic eruptions. Also a lot of earthquakes. Japan is a very active geologic area. They've got earthquakes, they've got volcanoes, all because of their location right there at the edge of the Pacific plate. They got a lot of mountains because of that, but also because of this process of magma kind of bubbling up onto the surface. You've got islands formed from that process. Iceland being an example. But because you've got this subduction zone here, it's jagged rock, so it's not always even. So where the Pacific plate and the Asian plate meet, you have the Marianas Trench, the deepest spot on the Earth, because that's where that plate is going right underneath the other one. Like I said, the Mid-Atlantic Ridge, it's the largest geologic feature on the planet. Its uplift is pushing the North American plate away from Eurasia, the African plate about 2 to 3 centimeters per year. The Atlantic Ocean is now 4,300 miles wide at the equator. So you take an average of an inch per year, that corresponds to about 225 million years. How can I tell that? One thing, the rock formations match up. The age of rock confirms it. Remember different types of fault lines. Convergent faults coming together, divergent line faults moving apart, transform faults, sliding against each other. Now, one thing they notice here about the Mid-Atlantic Ridge is how they can tell it is moving away from each other. Like I said, it's being pushed upward through the force of convection, and outwards it cools. So we've got the North American plate and the Eurasian plate being pushed away from each other. But where the Mid-Atlantic Ridge meets here the ocean, they're able to tell it's spreading apart by the different magnetic properties of it. Because we talked about the Earth's magnetic field. Every so often, it flips. The South Pole becomes the North Pole becomes the South Pole. The main magnets still work, the main compasses still work. Yes, just have to reorient them a little bit. But as rocks are cooled from this formation process, they orient toward the particular magnetic pole. So as the pole flips, you can see that magnetic change in the rocks, layer after layer after layer. So, an Atlantic Ridge pushing apart, you've got rocks nearest to it pointing towards the north magnetic pole. But at the same distance apart, you have, they flips to the south. Then to the north again, it flips back again, back and forth, and to the south. So you're able to tell it's been spreading apart at these rates, equally away from each other for millions of years. So the polarity, as it shifts, it's reflected in the rock formation in the Atlantic Ocean floor. Yeah, so we're able to tell a lot about these rocks, all sorts of properties. Crystal formation, composition, pressure, composition, magnetic properties. We're able to tell all of that. Now, the fractures in the rock along those movement, the fault lines, these little fracture lines, one of the most famous, again, the San Andreas Fault. At least one of the most famous for us. But what happens in that area also is, yes, sometimes there is volcanic activity. There's several chain of mountains in Oregon and Washington State that are volcanic in nature. For example, Mount St. Helens. This is in Washington. It's a volcano. 1980 it erupted. We learned a lot from that eruption. We also knew it was coming. We tried to warn people out of the area, but there's still a bunch of people got killed because of that. It was a beautiful area before the eruption, but basically it looked like the place had been nuked afterward. But in the 40 years since, it's started, all the trees and plant life and animal life started coming back in again. So the mountain looks a lot different, but nature rebuilds and recovers itself. Mount Rainier near Seattle. Huge mountain next door to Seattle. It's also a volcano. It's an extinct volcano. Or has been inactive, shall we say, for many centuries. There's fears that, yes, Mount Rainier could come active again. That caused all sorts of problems for Seattle. Like I said, there are volcanoes all the way up into Alaska. In fact, the most powerful earthquake recorded outside in the United States, recorded outside the lower 48, was in Alaska. So when they say California is falling into the ocean, it's not. It's just spinning alongside it. Just Southern California moving north. It's falling into the ocean. It's something I heard a lot when I was a kid, but it wasn't. Just an exaggeration. It's just spinning, just slowly moving north. Like I said, thousands of quakes every year. Most are not felt. In fact, what country is the most prone to earthquakes in the world? The United Kingdom. England, yeah. Scotland and Ireland. But most of them are way below one full magnitude. So most of them aren't even felt. Barely even recorded, but they're there. And as continental plates move, fractures and breaks in hundreds or even thousands of places. So the most dangerous earthquake-prone areas in the United States aren't on the San Andreas Fault. It's those little mini faults some ways away from the San Andreas Fault. They're finding these little mini faults, it's called micro faults, here and there in the Los Angeles area that could cause very serious earthquakes on their own. Because remember, it's moving rock, so it's brittle. It'll break. Pressure builds up, causing even more little breaks. In California, the quakes are usually named after the epicenter, what city or region or even neighborhood where it's closest to. So people living in California, they'll talk about, there's an earthquake or that earthquake. Just it's like we talk about the weather. Just not a big deal for them because they're used to it, because they're prepared for it, and the buildings are built to withstand those kinds of earthquakes. They know what to do. Just like any other part of the world you live in, you learn to adapt. If you lived way up north, say Minnesota or Canada, you would learn how to adapt to very cold winters. I think here in the South, you learn how to adapt to warm summers, hot summers, very hot summers. You live in Florida or along the Gulf Coast, you're used to hurricanes. You know what to do, you learn what to do, you learn how to prepare for it. I used to teach for this college in Florida, and about every year, right around Labor Day, they'd have to shut down for a couple of days because a hurricane's coming through. Nothing serious, no big deal, so we'll close down, we'll come back in a couple of days, everything will be fine. It's like nothing happened. You just get used to it. Like I say, it's another way that human beings use the earth is we are an incredibly adaptable species. We can adapt to just about any climate, any location, any natural hazard, anywhere on the earth. We know how to handle it. Next, say the powerful 1964 Anchorage, Alaska earthquake. So left dozens dead. Saying it was nearly a 9 magnitude quake, but it was centered 75 miles below ground. Deep quake caused a lot of damage across southern Alaska. In fact, it was such a strong quake that parts of the business district in Anchorage dropped 10 feet. It's a lot of rock moving around. Because that kind of intense power, that kind of order of magnitude on the Richter scale, that was a lot of energy released, causing things to drop. And of course, because there are breaks weakened to the point where magma can rise through through volcanic plumes. These areas here, they call them hot spots. Just little breaks where things kind of come through. That's why you have volcanoes in the middle of the Pacific Ocean. These tiny little cracks, these little plumes of magma are able to kind of rise through. And yes, how is it able to dig through solid rock? Well, hot liquid rock is able, heat rises, hot liquid rock is able to cut through solid rock. And there's a lot of gas pressure that builds up underneath that too. And so the Hawaiian Islands formed through this activity over a process of hundreds of thousands, millions of years. In fact, the islands are still growing today. That's how they're growing, through volcanic processes. There's even one off the southeast, just to the southeast of the main islands. It's still below the ocean. About 1 million years or so, enough volcanic eruptions, enough lava built up one layer after another, it will rise above the surface, be the newest Hawaiian island. So the Earth as we know it, it is constantly changing, constantly in motion. Not quickly, but it is. Some days it has these little growth spurts that are very dramatic that we see, like earthquakes or volcanoes, but it is happening. So next time we'll continue with chapter 3 and continue talking about different landforms and volcanic types and erosional types caused by geology. And if there are no questions, we'll call it a day.